Okay, now the record is on. This is pretty much where we left off the last time, okay? So let me recap again that this is our structure, okay? And based on the fact that we are going to use the sign convention clockwise positive. So here I am when I am in this, the first two equilibrium equations are just normal, right? So I don't have to mention that. But in the third equation, I will stick with the clockwise positive, and therefore I write MBA and MAB in the clockwise direction, and likewise for MCD and MDC. So in order to complete this free body diagram, you know that your RA and RD will point to the right. Okay, so if you may, now your entire structure will look like this. RA to the right, RD to the right, according to the direction of your moment. And you have the external force coming in here in this direction. So when you look at sigma fx, you can say that, okay, if I say RA and RD will be positive, my external force, which is 40, should be the negative. So that's how I obtain my sigma fx equal to 0, right? You just account for the direction and you can write everything on one side. That's very easy. That's how I use my sign convention. So RA and RD will be based on the clockwise positive direction. That means I can go ahead and write my RA and RD based on this free body diagram. Okay, and that is MAB plus MBA. If you cannot recall, just go back there. AB plus BA is going to be just 6 here and then 2.4, right? So there you have it. 6 EK zeta B plus minus 2.4, sorry, plus divided by the length, because you take moment at B, and it's the same goes for RD. Remember that these are based on the direction go to the right positive. So in the end, I can say construct my third equilibrium equation, the last one, by this plus this minus 40 equal to 0. Okay, now this is a very smooth sign convention application. So now I went ahead and solved for this. Now I got EK zeta B equal to minus 7.14286. I always talk about the sign convention, correct? So when you do the calculation, you may use this number, but you don't have to write everything down. So you can just write down maybe 7 point, this much. Don't go crazy about numbers. Okay, but when you do the calculation, just keep in mind that you can use the number with more decimals for your, say, for your complete and precise equilibrium in the end. But you don't have to tell anybody that, okay, it's going to be that many. It doesn't make you look good. Okay, however, in terms of academic, if you don't want to take any notes anywhere else, you can just put it there. I wouldn't mind, but in the end, when you answer for the moment, don't use so many significant figures. Okay, and EK zeta B. Let's look at the structure. It has some symmetric look at it. So yeah, it doesn't surprise you or me, I suppose, that EK zeta B turns out to be exactly the same as, oops, let's see, right? EK zeta C turns out to be exactly the same as B. Okay, and then EK delta. It's minus 59.52. The full number is minus 59.5238. That would be enough. Okay, and now you look at the numbers and see if it's possible. Okay, before you do anything. So now I'm just going to write this frame shortly here. You have the law push U and this. And EK theta B is negative, which means it is counterclockwise, right? Now you know that your frame is pushed to that side, so it's just gonna go like this. See, this has to come down a little bit. And is that counterclockwise? It is. So EK theta B and EK theta C looks possible. You see? So it moves in that direction. So it's counterclockwise, so it makes sense. And here is something like this. Okay, and look at this. Another one is EK delta. Now delta is, again, you see that your frame is now moving like that. So you see the sign is also counterclockwise. So now you see the sign conventions all make sense. What we have from our answer. So if you do use your sign convention, not like the way I constructed my third equilibrium equation here, keep in mind that in the end, it should give the answer that makes sense. So now with these numbers, I can go back and this is step number 5, right? End moments. That MAB is 57.14. What's the unit here? Oh, kilonewton meter. MBA is 42.86 kilonewton meter. And MBZ, you would expect it to be equal and opposite of this, and it is. So this particular structure tends to be, somewhat symmetric results, but keep in mind that this is because you have already lateral load. Once you start putting something on top of this as well, you are no longer going to have the theta B equal to theta C, okay? So keep that in mind. All right, and now I think the thing is pretty simple by now. That oops, it's the wrong one. So your MAB, now that's clockwise, okay? MBA is also clockwise because your beam, your column moves to the left, right? So your moment try to bring things back to the right. And for this is a negative, okay? And that another one should be like this, and another one should be like that, okay? And you can use this information to obtain your shear here. Okay, that's going to be how much? 57.14 plus 42.86 divided by the length, which is 5, right? And then because you don't have anything else, you're supposed to have this. That will give you exactly half of the 40, right? That's 100 divided by 5, so that's 20. So it doesn't surprise you as well, because these columns are the same. So in the end, you should have 20, right? So without doing anything, you should be able to say, your reaction here is going to be 20. But without the proper analysis, you would not know this moment. Correct? Okay. Well, the shear force bending moment diagram should be a piece of cake now. Okay. Is there any question about this? Hello? No question, I suppose. So let's move on to another example. I don't know why I just left so much space for that one, but not so much for this. Now we're going to have the problem. You see, that your columns are not of the same length. So in this case, if you don't do anything about the delta into the psi term, you're going to struggle with too many unknowns. Okay, so basically what will happen with this is this. The frame will go, it's hard to say which side it will go. So let's suppose that it's just going to go to the right. Okay. Now these three columns should share the same unknown, that is this delta. Okay, and so for step number 0, for your unknowns, say let's give this structure some name. Okay, so I'm just going to call this A, B, C, D, E, F. Okay, now we can say we have 4 unknowns. All right. They are theta A, theta B, theta C, and of course delta. Okay. Now you should know that your delta, you can write your psi name in terms of delta, right? Because these 3 columns have 3 different lengths, so the psi is going to be different, but delta is going to be the same. So I can go ahead and write here that if I look at the psi term, that's a psi, okay? Psi as this, psi, okay? So psi AD, now it is going to be equal to delta over the length of the member, which is 3, okay? And psi of BE, that's going to be delta over 4. And the last one, let's move them a little bit so they align nicely. Okay. And then the last one, psi CF, that would be delta over 5. So you have 3 psis, but the fact that you can write this psi in terms of delta, it makes your unknown down to 1. Okay. So the next step is the relative stiffness. So let's say my KAD is I over 3. My KBE, that's I over 4. KCF, that's it's 1.5 I over 5. And then we have KAB equal to KBC, that's 2I over 4. Okay, so the least common number is 12. So let's say K equal to I over 12. So this becomes 4K. This becomes 3K. This becomes 3.6K. And this becomes 6K. Okay? Again, you don't have to change this into relative stiffness if you cannot handle the least common number, that kind of stuff. It's not mandatory. Okay. Now look at this structure. We don't have the lateral load pushing it. Okay. What we do have is the unsymmetric condition where you have the load here. So the load is just here, this one. So whether you like it or not, the unsymmetric nature means that once this load pushes this frame down, it's going to move. Now we assume it's going to move to the right. It can move to the left. We don't know yet. So we're just going to have to wait for the answer, but it will move. It will have side sway problem. And your member will have the moment caused by joint displacement. That's the point. Okay, so here we need to calculate the fixed end moment because we have the load on the member. And FEMAB should be pretty automatic now that this is minus PL over 8. So it's minus P is 8 tons. Your length is 4 over 8. So just like that. So you have the moment minus 4 ton meter, and this is equal to minus FEMDA. Okay, so you see the most important thing is the identification of the unknowns and the relative stiffness and the load acting on your beam in terms of fixed end moment. Now they're done. And this is the basic stuff. It begins the real procedure here. Okay, step number 3 is the slope deflection equation. So it's going to be a lot then because we have so many joints. You're going to have the moment MDA, AD, that's 2, 3, 4, 5, 6, 7, 8, 9, 10. And have 10 terms. Okay, so let me try to squeeze everything in here. If you could, just try to find a way for you to see the frame and my writing at the same time. That'd be great for you. Okay, now I have to move down so you don't see the frame anymore. If you can see the frame when I write the moment equation, that'd be great. So we have MAB, okay, 2E, AB, AD, I'm sorry, that's AD, right? DA, not AD as well. You begin with D, MDA, it's 2E, and then 4K, right? It's a relative stiffness. I can save some time by, say, writing that my zeta D is equal to 0. Do I have to write that? Well, let's do it for the first ones so that you know. You have 2 zeta D plus zeta A minus 3 psi, and psi this time, you see, psi AD is delta over 3. Okay, and now this guy, zeta D is 0. Now we move on to AD. That's again 2E and 4K. Now we have 2 zeta A plus zeta D. Oh, that's D. Minus 3 psi. Okay, and again, zeta D is 0. Pretty simple stuff now. Oh, EB now. EB now is the moment in the second column, okay? And the relative stiffness is 3K. So it's 2E, 3K. Now I'm not going to write 2 zeta E anymore because now we know it's 0. So it's just zeta B minus 3 psi. This term is delta over 4. Okay, and you have BE next. Doesn't look like a B. BE. So it is 2E, 3K. Now 2 zeta B, zeta E is gone, so you have 2 zeta B instead. And minus 3 psi as usual, and psi is delta over 4 now. Okay. Next, DEF, right? FC. So it's 2E, this time is 3.6K. That's gonna be theta 2 theta f is 0, so you have theta c minus 3 psi. Psi, this term is delta over 5, and your MCF is 2e 3.6k and 2 theta c minus 3 and then delta over 5. Okay. Like that. Okay. Now we move on to the beam member, so to speak, horizontal member. We have MBC. Why I start with MBC? Let's start with MAB. Okay. MAB 2E 6K now. 2 theta A plus theta B. Remember that this is your beam member. Let's go back up. You see, this member, one of its joints, which is joint A, it moves to the side, right? So this member will have the moment due to joint displacement. But AB, the member AB and BC, they're supposed to stay flat. So this is one of the very common mistakes that students make. That is thinking that AB will have the joint displacement. Okay, AB stay flat. So yes, they move, but they move in the direction that they will not have moment. So let's say when you have a member like this, then you move it to the side, you don't have moment due to that movement, correct? So MAB, you don't have that term, but you do have the fixed end moment equal to -4. And then MBA is 2E 6K 2 theta B plus theta A plus 4. Now BC is going to be pretty similar to MAB, except that we don't have fixed end moment. So just 6K 2 theta B plus theta C. And then MCB 2E 6K 2 theta C plus theta B. All right. So now it's going to be quite of a mess. So I don't wish that we, I don't think it's a good idea saying that we try to track the mathematical endeavor here. So let me try to go over this as quickly as possible. Okay? Equilibrium equations. Now you have sigma MA equal to 0. Sigma MA equal to 0. Joint A, you have MAD and MAB. So it is this one and that one. Okay. Now you have to be very, very mindful when you do this. All right. You can try to track that later on, but let me give you the number. So it is 40 K theta A plus 12 EK theta B, then minus, we're going to have theta C too. So I don't know if it's possible for me to skip this. Okay, minus 8 EK delta. Okay, I try to leave some space so that I can write theta C around this space. All right. No, I deliberately did that. Oh, sorry. -4 equal to 0. And I move on to sigma MB. That's going to be a lot of fun because at joint B now you have 3 moments, MBA, MBE, and then MBC. And so in the end, sigma MB equal to 0 would give me 12 EK theta A plus 60 EK theta B plus 12 EK theta C, and then minus, say, 4.5 EK delta plus 4 equal to 0. So I can just move this guy a little bit here. All right, looks more promising. Notice this. See, that's 12, that's 12. So it looks promising, right? And because you can now see that your sigma MA equal to 0 doesn't have theta C. So you can bet that your sigma MC equal to 0 shouldn't have theta A, which is, that's a joint C, right? So you shouldn't have theta A anyway. So it's just gonna be equilibrium for the stiffness matrix, at least for that term. Sigma MC equal to 0. So that's MCB plus MCF, that's a CF, that's a CB. So you see, there is no theta A in these two. So here we go. In the end, it's going to be 12 EK theta B plus 38.4 EK theta C minus 4.32 EK delta equal to 0. Notice that, see, it looks really promising because we're going to have 4x4 matrix, and this is going to be your diagonal axis, right? Here's your diagonal axis. So you see, that is similar. You can say that is similar too. So far, so good. So it's down to the last one, which is going to take a lot out of us. So to have this in order, okay, let me go elsewhere and try to, because I'm running out of this anyway, so I need to add more. Current template is fine. So I'm going to come back here, but now you're going to need to establish the last one, which is sigma fx equal to 0. Okay, so now we don't have any horizontal load present, so it's pretty easy in terms of sigma fx equal to 0, because you're going to have just you can hd plus he plus hf equal to 0. So your hd is equal to MAD, right, plus MDA. Now you're going to have to be quite careful because for this member, it's 3 meters long. It's very ugly 3, so let me do it. Okay, so this guy, now you just add them up. It's just going to be quite straightforward. You go back up here. I'm not going to scroll back up again because it's confusing, but now it's just going to be a pretty similar term because you only have theta A and then delta. Okay, this is 24 EK theta A minus 16 EK delta over 3. Now HE is next. HE is going to be MBE plus MEB over 4. All right. If it helps, okay, let's just draw the free body diagram around here, maybe. And that's from this idea, okay? That's the same Fibonacci diagram for all three columns. So here we have 18 EK zeta B. Notice that, you know, this has only zeta A and delta. This has zeta B and delta. Over 4. And HF is now MCF plus MFC divided by its length, which is 5. My handwriting is a little bit bad now. That is 21.6 EK zeta C minus, you know, that's 8.64, right? My handwriting is pretty awful in my note as well. EK delta divided by 5. And you sum this up, all right? And what I have is going to be here, okay? Sigma. Hey, you guys need time to write this down, maybe? Just no response. So I have to assume that you can catch up, right? Okay, so now let me put sigma fx equal to 0 here. Just add them all up. And now you have 8 EK zeta A. See, that's 8, and that is also 8. Looks very promising. Okay, the second one is plus 4.5 EK zeta B. Again, very promising here. See, same number. Next is plus 4.32 EK zeta C. Ooh, look at that, 4.32, right? And the last one that cannot be helped because it's going to be different anyway. So it's minus 9.311 EK delta equal to 0. Ooh la la. So we have what you can say symmetric stiffness metrics, right? You can see it for yourself now that all the numbers kind of have a symmetric pattern. Now I'm just going to go ahead and solve it, give you the numbers. So EK zeta A is 0.149. For your reference, crazy numbers now. EK zeta B is minus 0.09733. EK zeta C, so clockwise again, 0.04174. EK delta 0.10062. So with these numbers, you can take the sign convention and go back and look at your frame whether or not it's possible. So you should do that. Okay. Those who refuse to acknowledge your results mean that you are afraid and because you think it may be wrong. And when you think it may be wrong, you cannot confront it. You're going to have the wrong answer in the end anyway, right? So zeta A is clockwise. Is that possible? You think? Because you have the load present here. So this portion should come down. So yeah, that's clockwise. So it is very, 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 very plausible. Correct? Now B. B is counterclockwise. Is that possible? Let's go to draw. Counterclockwise is in this direction, right? So let's go back here. Counterclockwise, it should be something like this. So that possible? It is also possible, right? And then C is positive. So C is clockwise. So again, what do you think? Oops, that's the wrong color, right? I should use this one, right? Instead of just going back and forth. So now it is going up. So you see, it is very, very possible. And EK delta confirms that it actually, go in this direction, because now your psi is positive, because your delta is positive. So they all move to the right like that. Okay, so you see your answer makes sense. So if it makes sense, we can go and try to end our calculation by substituting all the answers back to your moment equation here, right? It's going to be a long word a little bit. So let me give you the answer. Step number 5, end moments. I don't like this example very much because it just write and write and write and write and write. I'm not gonna write the equation because just to save some time. Okay, you can do it for yourself. You can just put this back in your MBA, and this is 0.39 ton-meter. Okay, MAD. Okay, MAD now. MAD is 1.58 ton-meter. Okay, and just try to couple this together. MAD, they should be with MAB, right? Because the joint A contains 2 members, so this should be equal and opposite, and rightly so. Okay, so that ends it. Now let's move on to you may want to look at the next opposite of MAB, that's MBA. MBA is 3.46 ton-meter. Now MBA, you're gonna have to compare this with say MBE and MBC, right? So let's go for MBE here. MBE is minus 1.62 ton-meter, and the last one is MBC. It's minus 1.84 ton-meter. Okay, and this guy, the summation of this moment that is 0. Okay, and the opposite of BE, that's EB. So let me write here. MEB, that's minus 1.04 ton-meter. Okay, and BC, that's okay, BC should be, that's the opposite of MCB, right? MCB, that's only minus 0.17 because it's far away from where the load is. So it's only normal that you see the number so small. MCB, and then opposite of this was CB. Now I'm confused. So many. Hang on a minute. Okay. CB is CF. Okay. CF. CF is 0.17. Okay. CB and they're supposed to be equal and opposite. Okay. So that's 0.17. So see, it's 0, and then this last one is MFC, right? MFC is only minus 0.13 ton-meter. So you see, actually, after you get the answers, this is like a repetitive procedure, you know. You just put all your answers back to your moment equation. So the key is right here. If you can establish the correct equilibrium equations, the rest will just fall into places if you are good enough to keep your mathematics. Okay, sigma MA, MB, and MC themselves are pretty straightforward. The tricky one is sigma FX because it requires a lot of work for you to go through. Okay, and here that's your extra work. And once you have this, is nothing. Just complete the step number 6. How do I name step number 6? How do I call it? The reactions, maybe. How are you going to call it? The reactions. Shear. Complete free body diagram. Now you just put them in here. So let's begin with AD. AD, you have 1.58, that's clockwise. So we use different color. So you can see it's clockwise here. And then DA is positive, so it's clockwise. Okay. Now the next one is, let me try to bring this down a little bit. It's too high. Like that. And then next one is DE. You have, of course, equal and opposite. Where's DE? I'm sorry, that's not DE, AB, that's more like it, AB. So see, it's minus 1.58, so it's counterclockwise. The next one is BA, that's positive, so it's clockwise. So that, and don't forget that you have 8 tons as well. And 1.58 here. And then this is 3.46. The next one is BE, right? And then this is BE, that's negative. BE here. So it is counterclockwise. 1.62. And then EB, that's also negative. 1.04. Next one is the BC, right? BC is negative here, so it's counterclockwise again. 1.84. Where's my arrow? Okay. Next one is CB. Right, CB is also negative. Okay, counterclockwise. Only tiny number now. Because you just have the load here on BC, the rest just has the moment simply because they are connected to each other. Not much. Now you should have this in the clockwise direction for CF, which is, yeah, that's a number. And then the FC, that's counterclockwise. So, but when you come into this part, it's just the basic statics for you now, right? So this thing should not bother you anymore. I hope not. But let's say I give you some numbers. You can perhaps practice. That's going to be pure shear, right? No any additional force. So it has to be equal and opposite. Right here as well. This is the counterclockwise moment, so you have clockwise shear here, 0.67, 0.67. Likewise, well, this is tricky, but the total, the summation of the moment gives you the clockwise, so you need to have counterclockwise shear, and the number is very, very small because this is far away from the action. And your action is here, remember? And here is another pure shear. The total moment is counterclockwise, so you better have clockwise shear here. It's just this one where you need to take care of the external force as well. Don't forget that. And in the end, this is,
me.
yep.
For the first member, it should be AD, right? Not DA.
Oh yeah, right. You're right. Yeah, I swapped the place, right? Thank you. So it's A on top, right?
And could you indicate the magnitude for DA, please? Which is 0.39.
Which one?
DA moment. Right? You didn't write the magnitude. Right?
Okay.
Just, okay.
Sure, sure. The number is, what's it? The 0.39, right?
Yes, yes. Okay, thank you.
Thanks. All right. So let's get this shear then. With 3.53 and 4.47. Okay. Wow, this is quick. Actually, okay, that's should be the end of the first break. Let me pause the record first.